whether it's between the nucleus of an atom and its electrons, whether it's between the nucleus of an atom and electrons in a covalent bond, or whether it's between ions and each other. We've talked about electrostatic forces in different ways before. Intermolecular forces are a particular example of these, in that we are talking not so much about electrostatic attractions that exist within a molecule, but rather forces that exist externally from the molecule to other molecules. Now, because these are external forces as opposed to internal forces, they are naturally going to be weaker than bonding forces are. The one great attribute that a nucleus has to its electrons is space. They are really close to each other. Molecules, on the other hand, aren't necessarily going to be as close to each other as a nucleus is to its electrons. And that's going to weaken it by distance naturally. The other thing that we should know is that these are secondary kinds of forces. Bonding forces are primary. They are first and foremost in consideration. These are alternative forces. These are extra forces that exist, again, outside of the molecule itself. Now, one of the things that we can pick up on is that if we start looking at things from a perspective of density, it becomes very apparent very quickly that gases are going to have a real difficulty when it comes to intermolecular forces. And the reason they're going to have such a difficulty is, by contrast, you can see that the densities of gases are somewhere between 100 and 1,000 times less dense. What does that mean ultimately on the molecular level? Spacing. If something is that much less dense than something else, its molecules are going to have to be that much further apart from each other than they would be if they were in a more condensed phase. And so gases, because of that density, because of that spacing, we don't tend to think of gases as having very much in the way of intermolecular forces. In fact, we kind of consider them, and we'll talk about this next week, we kind of consider that they don't have any intermolecular forces at all. Liquids and solids, on the other hand, we can see that their densities are different. Solids do tend to be more dense than liquids, water being a very curious exception. And we'll talk about why it's an exception when we talk about hydrogen bonding. But for the most part, what we see is that solids tend to be a little bit more dense than the liquids do, but the gap between them is not nearly the same as the gap between liquid and gas. What we have in the picture here is usually a matter of organization. Liquids tend to be a little bit less organized, a little bit more disordered, and that disorder causes them to not be able to be packed in quite as tightly. Solids, on the other hand, tend to be very ordered and very arranged in their makeup. And that allows them to have greater density overall, usually. But we can see in both cases here, we're going to have molecules that are very close to each other. We're going to have molecules that are touching each other. And from that standpoint, intermolecular forces are going to have an impact on these kinds of substances. So we tend to think of intermolecular forces as being either a solid or a liquid kind of phenomenon. And we can see the differences here between them. Because those intermolecular distances are shorter, because these two are a lot closer together, they are going to feel each other more. And the intermolecular forces that exist among them are going to be greater as a result. Let's take a moment here and make sure that we define our terms, and we do so very precisely. So thus far, we've presented forces inside of substances as intramolecular forces. Intramolecular forces are the forces that are governed by bonding. So whether those are forces of covalent bonding, again, the attraction between nuclei and shared electrons, or if they are the result of ionic bonding, the electrostatic attraction of a positive ion to a negative ion and vice versa. Those are all considered intramolecular forces. Those are the forces that hold a molecule together, hold a molecular unit together, hold an ionic crystal together. They are strong and attractive. Intermolecular forces, on the other hand, are ones that are associated between molecules. So, if we're going to think of key words here, the intramolecular force is within a molecule. We call it collectively bonding. Intermolecular forces are between molecules. And so, again, specifically, we're talking about solid phase and liquid phase kinds of things, because those are the ones that are going to be close enough to have those attractions. As we talked about in modules 7 and 8, bonding is all about chemical nature. Bonding is all about chemical properties. So when we talk about intramolecular forces, we are usually talking about chemical kinds of properties. I put this substance with another substance, and they come together and they make new bonds to form this new substance. Intermolecular forces, on the other hand, they are focusing primarily on physical properties. And so the physical properties that we will end up focusing on a lot here are viscosity, boiling point, vapor pressure, melting point to a lesser extent. So we're going to be talking a lot about phase changes on Wednesday. And that's going to be kind of our jumping off point for describing some of the physical properties that we can explain away with intermolecular forces. Now, when it comes to intermolecular forces, there are 5 types of intermolecular forces, and we're going to focus primarily on 4 of those types. The 5th type, the van der Waals forces, those are kind of an interesting little subset of the subset here, where we are talking about forces that are existing between molecules of actually different types of forces. We'll cover that a little bit more detail later on. Now, one thing you should know about this particular list, it's not in any particular order. So these are just 5 types of intermolecular forces that we're going to look at. But this is not a list that is in any kind of order in terms of strength of force or lack of strength or even alphabetical. It's just a random list here. We're going to talk about each of these kinds of forces in turn, though. And we're going to start with the weakest of these forces, which is the London dispersion forces. Now, one of the reasons we start with London dispersion forces is that London dispersion forces are in every substance. Every substance displays London dispersion forces in some kind of way. Now, it does so because London dispersion forces are primarily focused on the movement of electrons. Since every substance has electrons and all those electrons are capable of moving, that means that regardless of what kind of substance it is, atomic, molecular, ionic, you name it, those electrons are in motion. And being in motion, it possesses the ability to create what we call a temporary dipole. Also known in this case as an instantaneous dipole. Instantaneous because it can form in an instant and also disappear in another instant. So I'll give you a second to copy down a couple of things there. I will tell you, from a conceptual standpoint, London dispersion forces can kind of be the toughest to get our brains around. We're going to talk about dipoles, here in a couple of minutes. We've talked about molecular polarity. So the context for that already is there. It exists. And we can see how those positives and negatives attract each other, molecule to molecule. But London forces can be a little bit hard to kind of put our heads around because, well, it's a little bit more abstract. So we're going to try to simulate that here in the classroom. Let's see, how many do we have today? Right. We've got 12 people in this classroom today, excluding myself. Right. What I need everybody to do, I need everybody to stand up here for a second. This is going to seem so hokey, but I'm going to tell you, it's going to give you a picture that's going to be easy to remember. So let's see, there's 12 of us here today. So Donnie, Madison, we're creating this thing. Okay, if I was splitting this classroom in half, right between Madison and Shelby here, and you individuals represent electrons inside of our theoretical molecule. Right now, we have an even split. There are 6 electrons on this side, which is your left, your right by left. There are 6 electrons on this side, your left by right. This would be the epitome of what we would call a non-polar molecule. Because after all, the distribution of electrons is even. Now, when I say go, we're going to keep on the roll of electrons. You're going to move around a little bit until I tell you to stop. So I tell you stop, reach where you are, we're going to reevaluate the situation. Go. All right, stop. Perfect. Perfect. Okay. Here I see Peter on that side, Piper on this side. Okay, remember we started at 6 and 6, right? Now it's 8 and 4. 8 on your left-hand side, 4 on your right-hand side. You have, in a matter of about 8 seconds, a temporary dipole. This side over here, where there's a greater electron density, this would be the slightly negative side. This side over here with fewer electrons would be the slightly positive side. Now, if I put you into motion again, which I'm not going to do, no. But it would be pretty easy to see how just through the random motion, yeah, you can go back. It would be pretty easy to see that just through the random motion of you moving around, we would very easily go back to non-polar, or even polar with the negative on the other side of the classroom. That's the nature of these instantaneous or temporary dipoles. They exist, but not for very long. Now, here's the other thing that we cannot simulate. As you're moving around and creating these temporary dipoles, let's just imagine that there is a classroom over here to this side, and a classroom over there to that side. In that moment when you split up, and you had a negative on the left and a positive on the right, that doesn't just happen without any kind of ramifications. Same thing would happen to the classroom over here on the left. With the extra electrons over here, it's going to force the electrons in that room to do the same thing. Now I've got a negative side and a positive side near each other. They attract, albeit briefly. Same thing happens over here. On this classroom on the other side of us, it feels the lack of electronic over here, the positive pull over here, and it attracts more electrons to that side of the room on that substance. I get a negative over here and a positive there. They attract, although it's brief. So what we can kind of pick up from this is that those kinds of attractive forces do exist. But we can understand why they are also weak. Because just as quickly as we got all those little dipoles to form and attract each other, the dipoles all go away and they kind of go back to where they were. Because all substances have electrons, they all do experience London forces. However, substances that are also polar tend not to really focus too much on the London forces because they already have permanent dipoles in place that create these more permanent kinds of attractions. So where we tend to focus the most on London forces is in nonpolar molecules. Because in nonpolar molecules, these are the only forces that exist in that molecule. Now, what are some factors that can kind of play into how big are the forces going to be? There's two factors that we look at: size and shape. For size, more is better. The more electrons that we have, the bigger the substance is, the easier it's going to be to create those dipoles. So we did an experiment in here with the 12. Do you think it'd be easier to create a dipole or harder if there were 30 people in this classroom instead of just 12? Easier, right? Because you got to think about it from a combination standpoint. There's one combination, 15 on each side, that would be completely non-polar. There are dozens of combinations that would not be polar. 14, 13, 17, 17, 13, 18, 12, so on, so on, so on, so on, so on. As my number of electrons increases, so does the possibility of getting a temporary dipole. Now, rather than count up electrons, we can simulate that, we can estimate that using molar mass. Higher molar mass, higher London dispersion force. The other impact here is shape. With shape, we're talking primarily about surface area. And so there are a couple of things that we would want to consider. First of all, any planar shape is going to have way more surface area than a three-dimensional one. So if I'm looking from a molecular standpoint at a linear substance or a trigonal planar substance and comparing it to a tetrahedral, there's no contest. Those 2D shapes are a lot easier to get close to each other than any 3D shape would be. But where we see this argument the most often is in situations like this, where I've got what are called isomers, that is substances that have the same molecular formula, same molar mass, but they're different structurally. Here I've got all four of the carbons all stretched out in a chain. On the left here, I've got the 4 carbon atoms and they're kind of bunched up together in a cluster. The chain, where they're all stretched out a little bit, has greater surface area than the cluster does. What does that mean? Well, in this case, it's about an 11-degree difference in boiling point. So I got the same substance, same chemical formula, but simply changing the shape from linear or from branched to stacked is worth 11 degrees in terms of boiling point. All right, let's look at this question. Which of these substances would only have London forces? So with one minor modification here, let's ignore that typo there, it's KNO3. What is this question really asking? Polar, nonpolar, exactly. If I'm looking for something that only has dispersion forces, I need to find nonpolar substances. So if I look at potassium nitrate, do I find a nonpolar substance in potassium nitrate? Potassium nitrate, just by the way that we name it, we know that it's ionic. Ionic is polar to the extreme. So polar that they're not sharing it anymore, they're actually transferring the electrons from one side to the other. The attractions there are super strong. What about hydrogen iodide? Polar, yeah. So we know it's not ionic. Hydrogen and iodine are both nonmetals. But from an electronegativity standpoint, we also know there's some unevenness in that sharing. So those two aren't correct, which means D can't be correct. CCl4 is our correct answer. Now, how do we know that? Well, we've got to go back to drawing. I've got a tetrahedral here, tetrahedral with the same bond in all 4 directions. That is by its very definition symmetrical. And remember, symmetry means nonpolar. All right, let's move into the next one. These ones are a little bit easier to put our head around because we've already talked in some kind of way about these. Dipole forces. Dipole forces are, we've got polar molecules that are attracting each other. So the whole idea that we brought into last unit about dipole moment and polar nature of a molecule gets applied directly here. The positive side of that polar molecule attracts the negative side of a different molecule. So if I'm looking at HI, which we saw in that previous example, the hydrogen is slightly positive because it has a lower electronegativity. The iodine is slightly negative because it has a higher electronegativity. And we can see that the positive and negative are attracting each other continually. Now, general good rule of thumb here that we want to look at. The more polar the bond is, the more attracted they are to each other, the stronger the intermolecular forces are going to be. That's a good general kind of case rule of thumb. Now, how do we measure that polarity or polarizability? This is something that we talked about in Module 8, dipole moment. So if you recall, we talked a little bit about dipole moment here in the kind of the grand scheme. We can now look at its effect here. So here I have silane SiH4. It's tetrahedral. Everything's canceling itself out. Net dipole moment here is 0. And we can see that the melting point and the boiling point are low, as you would expect for something like that. Here I have pH 3. In the pH 3, not only do I have electronegativity pointing to that center atom, I also have that lone pair on top of that phosphorus there that is going to continue to drive that dipole moment up. So I've got a dipole moment here that is non-zero. What does that mean? Pretty significant. We're talking about a 50-degree difference in melting point, about a 25-degree difference in boiling point. So if we ever had any concerns about polar versus non-polar, which ones are more attractive, it's pretty clear and obvious when we get to the data that simply having a dipole that is permanent is going to have a massive effect on the physical properties compared to one that is not permanent. Now for the hydrogen sulfide, in addition to, again, the electronegativity, we also have those two lone pairs on that sulfur that are going to continue to drive that dipole moment up. We see a considerable increase in dipole moment there. What does that do? Well, same thing. That increase in dipole moment, 50-degree jump in melting point, and again, about a 25-degree, a little bit less, jump in boiling point. Now, mass-wise, they're about the same. So London dispersion forces aren't playing any role here at all. It's only the polarity of the molecule itself. Increase my dipole moment, increase that polarity, and I see that these melting point and boiling point are going to raise in temperature as a result. And we'll get into more of the whys and hows on Wednesday. Here's our next interesting kind of phenomenon. We've got hydrogen bonding here. Now, hydrogen bonding we can think of as kind of a specialized version of polarity. Two conditions have to be met for hydrogen bonding. First of all, you have to have a polar molecule. So if the molecule itself isn't polar, this doesn't matter. The second point doesn't matter at all. The second thing that we have to have is that we have to have a highly electronegative bond present. And so what constitutes a highly electronegative bond? Well, it's got to include one of the three most electronegative atoms, nitrogen, oxygen, fluorine. So done because they are very compact in their charge. That second energy level is tiny compared to the third or the fourth or the fifth or the sixth. So compactness of charge, highly electronegative, and polar. So in particular, we're looking at OH bonds, FH bonds, or NH bonds, plus a polar molecule. That's what gives us hydrogen bonding. Have to have both of those conditions. Polarity plus one of these types of bonds to get hydrogen bonding. This kind of bonding is super powerful compared to normal dipole-dipole forces. And as a result, it has a considerably larger effect on physical properties than just simple dipole moment alone. So how can we illustrate this? Well, let's take a look at this graph here. This is a graph of the different boiling points for the chalcogen and halogen hydrides. So we're talking about group 16, 6A, and group 17, 7A, and their bonds to hydrogen. What we would expect based upon London dispersion forces is that as we went down a column, dipole moment probably isn't going to change significantly. The hydrogen, or excuse me, the dipole moment between hydrogen and sulfur, hydrogen and selenium, hydrogen and tellurium probably isn't enough to see a big difference. What's making this upward trend is this is where we start to see the impact of London forces. So if I'm looking at a series of molecules and I determine from a polarity standpoint, they're all about the same. This is where hydrogen bonding, or excuse me, hydrogen bonding. This is where London forces can play a role. Like I said, London forces don't usually make that big of a difference in polar molecules. But all things are considered even, London forces can make a difference because they can tell us what additional forces are also being factored into the physical properties of this substance. So if I go down a column, I'm going to see sulfur, selenium, tellurium, more mass, more electrons, more London forces. I'm going to see a gradual uptick in boiling point related to those. Because again, polarity-wise, they're about the same. They're in the same group. And even though they are bigger, that's not going to make that big of a difference in the dipole moments. Same thing for the halogens. The main difference in this trend here is just London forces. But that doesn't explain why this is a hockey stick instead of just a simple linear trend. Why is water so much higher in boiling point than these other ones? Why is hydrogen fluoride so much higher in boiling point than hydrogen chloride? The answer there is hydrogen bonding. The fact that we have these additional forces in addition to the dipole makes these molecules that much more attracted to each other than they would be otherwise. So that's why water boils at 100 degrees instead, according to the periodic trend, we expect it somewhere around -75. Hydrogen bonding makes a big difference there. It also is, fun fact for the day, hydrogen bonding is also the reason why water molecules, why does water float as ice instead of sink? Well, the hydrogen bonds in water, as water is starting to solidify, they expand and they lock in that expansion. So what you get is water molecules taking up more space as solid than they were as liquid. Net consequence of that is if the volume is bigger but the mass is the same, density goes down. So it is the hydrogen bonding in water that ultimately means water is going to be less dense as a solid than as a liquid. It's a weird phenomenon. And it kind of goes against what we would expect for that reason. All right, last type of force that we're going to talk about are the ion dipole forces. Ion dipole forces, so named because they are the attractive forces that exist between an ion and a polar substance. Where we talk about this most is in water. Why does water dissolve ionic compounds? Well, it's mainly because of the ion dipole forces that are being made here. So if we go all the way back to module number 5, when we talked about solution, talk about the idea that when a solution is made, 3 things have to happen. The water molecules have to come apart, make room for the solid. The solid molecules have to come apart so that they can actually dissolve. And then the solid and the solute and the solvent have to attract each other. The only way that that happens is if, energetically speaking, it's more favorable to have them combined than to have them separated, which means that the attractive forces in the solution have to be greater than the attractive forces in the solid. And that is where we get into the idea of our solubility rules. Why is manganese carbonate insoluble in water? Well, the attractive forces between the manganese ions and the carbonate ions are greater than the attractive forces between the manganese ions and water and the carbonate ions and water. So they stay separated rather than coming together. Why does an ionic compound ever form in the first place? Well, what we have to consider is that this sodium and this chloride, they do attract each other, and they attract each other very, very well. Do they attract each other enough? One thing that we have to consider, ion dipole forces are multiplicative. I don't just have one chloride attracting a water molecule. I have a chloride that's actually attracting 6 water molecules. You got 4 here in the diagram. The 2 that aren't shown, 1 here in front and 1 here behind. The collective ion dipole forces between that chloride and the 6 waters that it attracts are greater than the collective attraction between the sodium and the chloride itself. That's why it breaks apart. That's why it becomes soluble. Now, one other thing, I want you to burn this image in your head. Look how the waters are oriented. For the positive ion, it's attracting the negative pole of the water, the oxygen. For the chlorine, the negative charge is attracting the positive end of the water molecule, the hydrogens. Keep that in mind because that's a really important kind of sub piece to that perspective there. So that's all that we have for today. So that should be enough for you to do the homework assignment that's due tonight. Give us a really great launching off point for Wednesday. Make sure that you hit the stoplight question on the way out today, and have a good day.